Memory is powerful but also dangerous. A single out-of-bound write can overwrite return addresses, function pointers, or even critical system data. It can lead to crashes, silent data corruption, or even full system compromise. In fact, some of the most famous security vulnerabilities like Heartbleed or the original Morris worm exploited bad memory handling. Welcome back to what every programmer should know about the memory. Today we are diving into the dark side, buffer overflows, dangling pointers, and how modern systems use tricks like ASLR to fight back. I'll show you real code, real risks, and how to write safer programs. Let's go. A buffer overflow can happen when you write outside of the array or memory buffer. It's one of the oldest and most dangerous bugs in C. Here's a simple example. Let's define in the main program a character named as a buffer with the size of 8. We copy this string into this buffer and then we output what buffer includes. What's going on here? The buffer only holds 8 bytes, but strcpy happily copies 25 bytes into that buffer, including the null terminator. That means memory after the buffer gets overwritten. What is after it? Maybe another variable, maybe return addresses, maybe something critical. We don't really know. This is how classic exploits work. If an attacker can control the input and you use gets, strcpy, or unsafe sprintf, they can write malicious data, like shellcode, into memory and overwrite a return address. When the function exits, it jumps to the attacker code and that is game over for your system. Modern systems try to protect against this using stack canaries, special values placed next to the return addresses. If a buffer overflow changes the canary, the program crashes before the attacker gets control. You can enable a stack protection in GCC like this. You can add a flag fstack protector all when you want to compile your program. But even then, some overflows slip through, especially if they target heap structures or internal metadata. Heap-based overflow works the same way, but instead of writing past the stack buffer, you corrupt the memory in the dynamic allocation. This is especially dangerous when memory metadata sits next to your buffer. Here is an example. We define a character pointer using malloc with the size of 16 bytes. We write this string to this buffer, which is obviously bigger than the buffer size. We printf the buffer and at the end we free the buffer. Again, no size checks. If the heap allocator stores bookkeeping data after the user buffer, you might overwrite it. The next malloc or free can crash. Or worse, it could be tricked to do something malicious. Even worse is use after free. So in this example, data is the pointer of integer, and with malloc, we allocate the size of integer to it. We assign 42 to data, and then free the data. But then we try to use the data after freeing it. Here the memory was freed, but we are still accessing it. Sometimes it will print the right value. Over time, the allocator has reused or unmapped the memory. This causes unpredictable crashes, or in security terms, undefined behavior. An attacker can exploit. Valgrind can catch such kind of bugs, or compile with sanitizer, like the flag sanitizer equal address. Run it and the sanitizer will scream the moment you touch free memory. Another subtle and dangerous mistake is dangling pointers. That's when you keep a pointer to memory that is already been freed. For example, in this code, we define a global as an integer pointer. In the setup function, we allocate temporary pointer with the integer size. We assign the value to that temporary pointer and we give an address of temporary to the global. And then we free the address of temporary pointer. In the main function, we call the setup, and when we try to allocate the value to the global pointer, we reach undefined behavior or dangling pointer, since we free up the address of the temporary variables in the setup function. But the problem is that this compiles and it runs, and it might even appear to work, but it is corrupting the memory. The memory pointed to by global is no longer owned by you. The OS or allocator might have handed it to someone else already. A related bug is double free. You allocate an integer pointer, then you free that pointer 2 times. Freeing the same memory twice usually causes a crash. But in older systems, Attackers could use it to corrupt the allocator metadata and hijack the execution. Again, address sanitizers and valgrind are your friend. They catch this instantly and tells you what went wrong. So how do modern systems protect themselves against these kind of bugs? One of the biggest weapons here is ASLR, or address space layout randomization. The idea is simple. Every time your program runs, the layout of memory is randomized. Stack, heap, libraries get loaded in different addresses. This means if an attacker wants to jump to a known function, they cannot rely on fixed memory addresses. Even if they manage to overflow buffer, they don't know where to jump. Exploiting becomes much harder. Here's a quick way to see ASLR in action. You can cat the process directory with the process ID of your application in the maps directory. Then run the program again. The memory layout will be different. ASLR can be disabled and often is in embedded systems or real-time systems, but it is on by default in modern Linux, Windows, and macOS. Combined with stack canaries, DEP or data execution prevention, and control flow integrity, ASLR is part of a multi-layered defense strategy. It doesn't fix the bugs, but it makes the exploiting them much harder. So what we can say is that memory is fast. It is powerful, but it doesn't forgive the mistakes. One write outside your bounds and you are in danger zone. Buffer overflows, use after free, dangling pointers, double freeze. These aren't just bugs. They are entry points for attackers. They are the foundation of exploits. But with modern tools like sanitizers, valgrind, stack protection, and ASLR, we have the means to fight back. The best way to defend yourself is to write safe code. Use bounds check functions, avoid raw pointers when you can, and use languages with safety features. Or if you are using C or C++, test aggressively and review every line that touches the memory. If you find this episode helpful or even terrifying, give a like and subscribe to not miss the next videos. You can also share your war stories with memory bugs in the comments down below. Until the next video, good morning, good afternoon, and good evening. Bye.